So first of all, I would like to thank the organizers for organizing this wonderful conference in such a beautiful place, and I'm grateful for them inviting me to give a talk here. I'm going to talk about cosmology and the string Swampland, which is a talk based on, first of all, I have to get this straight. So it's a talk based on two papers. One of them is actually just came out with Georges Obi, Hiroshi, Lev Svodinenko, and myself, and also the other one, which is going to come out in a few days, hopefully with Pratik Agrawal and Georges Obi and Paul Steinhardt. So, so the plan for my talk is, first of all, I want to discuss the evidence we have for the existence of de Sitter space. And I motivate discussion based on observation, and then I talk based on this discussion a new swampland condition, which is a lower bound on the gradient of a potential for scalar fields in quantum theories of gravity, with bound being proportional to V itself with some positive constant. And then I talk about cosmological implication of two swampland criteria for past, present, and future of the universe. One is this criteria, and the other one is a criteria on the bound of the range on the scalar fields. So before I start with the discussion, I should point out that this talk is based on really speculation, but I hope that the speculation has a strong motivation in terms of possible observation in the real universe, which is what we hope to do in string theory. Of course, the rain during the lunch was not a promising sign. So hopefully this will So hopefully this will not be in that category, we'll see, but at any rate. So it is speculation, but I'm going to shamelessly discuss it nevertheless. I think we need discussion which hopefully connects string theory to observed universe, and this is in that hope, in that direction. So I hope you allow me to entertain this speculation here. Okay, so why de Sitter? Well, the answer is because we live in one. If I ask this question to any of you guys, most probably the answer I would get would be something like this. We live in one space called de Sitter. So your theory better give that to us, otherwise your theory is wrong. That's the reaction most people, including I, would have had. Because we say, well, we have a positive cosmological constant, so you have some kind of potential. We know in string theory there's no free parameter, so there's got to be some potential of some fields with a minimum, or at least a local minimum, at some positive value, which is our present cosmological constant. This is the present picture of how we try to connect string theory to our observed universe with the lambda, which is very small. Question comes, why not rolling scalar potentials a la quintessence models? Why don't we imagine having a situation like the cosmological constant on a rolling potential instead of having a fixed value? Well, there are various arguments and there are various motivations why people do not like this scenario, and I want to review those arguments. First of all, the scalars will be useful if they couple to something, and typically in string theory, we are very sympathetic to that. If you have a field, it's not going to be possible, or we don't know examples where it doesn't couple to anything. It better couple to something, and therefore it's natural to think that observables will be affected. For example, you would think that the fine structure constant will vary. But there are strong bounds on these things, like the variation of the fine structure constant. The percentage change of it from z equals to 1 to now is less than 10 to the minus 6, which is extremely tiny. So this suggests that if there is such a thing, this scalar is not changing these observables in any way. Another problem is that if you have this scalar field, then the coupling, and if it couples to our matter field, it gives rise to new forces between the matter field. This is almost like a very light scalar field, and you get some fifth force. And the fifth force, if you look at astrophysical observations, it will give rise to apparent violations of equivalence principle, because there will be extra force other than the gravity in the game, and so you will get new things. And there are strong bounds on the apparent violation of the equivalence principle. So there are also strong bounds on the fifth force. So these are two arguments leveled against this picture. But from a string perspective, these do not look like good arguments. So first of all, it's true that scalar fields should couple to something strongly. That string theory tells you that. But that something may not be the standard model. So it could be that we have a compact manifold. The standard model is coming from a local region of the internal geometry, and then there's some other sector, the dark matter, for which the scalar couples strongly. So in this case, we could say that if we are in a rolling situation, that rolling one anticipates dark matter. So it's a prediction of dark matter instead of saying it's a negative thing. So it's the exact opposite. But there is another strange feature of quintessence models. Not only the value of the cosmological constant is small, 10 to the minus 122, but also if you want to make the quintessence models work in Planck units, the gradient should be bounded also by about 10 to the minus 122. This looks like double fine-tuning. However you want to fine-tune V, you have to, in addition, fine-tune gradient of V. So the easiest answer you would say is 0. Why do we go to such a distance? Unless somehow the gradient of V and V are somehow related. If there is a natural bound of the form gradient V of proportional to V, this alleviates this double fine-tuning. Unlike ADS, constructing de Sitter vacua, even metastable ones in string theory seems very difficult. Now here, I want to make clear what I mean by this. I do not mean trying to get the observed universe in 4 dimensions with standard model, with de Sitter, etc., etc. That's a tall order. Rightly so, people will say, this is a hard thing to do. How do you expect me to get the exact answer? No, I'm not asking that. I'm saying there's no single example of de Sitter anywhere in any dimension, in any string compactification, which is simple. So in other words, take 10 dimension, 9 dimension, 8 dimension. No, I don't care about standard model, nothing. Just give me one example of de Sitter which is trustable that I can actually compute and check. We don't have any examples. Well, despite this, there have been heroic efforts, notably the KKLT and similar follow-ups. There have been attempts and there are proposed scenarios of how you can achieve this. And I think there are also criticisms leveled against them. So I think they are at the level of proposed scenarios for construction, not rigorous construction, so we do not know the status of them yet. It could be that this is true and this scenario comes to fruition, so I cannot rule that out, and we do not know that. But given that we do not have a strong, sure way to assess that, it is worthwhile to contemplate the opposite. In fact, if you want to construct de Sitter vacua, one needs to do something at least a little exotic. For example, Maldacena and Nunez give a simple no-go theorem in the limit of M theory supergravity. So you take the M theory in supergravity limit, where you ignore the higher curvature corrections, and in that context, they simply and beautifully show that there is no de Sitter in M theory vacua, no matter what dimensions you take. This, of course, does not mean you can never get de Sitter from M theory, because you can have high curvature corrections or situations where the curvature of the manifold becomes Planckian in M theory units. So that does not prove it, but still, the simplest thing that you might think does not give you a de Sitter vacua. So let us dare to ask, what if there are no critical points of V with positive value? If so, the next natural question is how close we can get to gradient of V to 0. If gradient of V is 0 is not achieved, maybe there's a bound away from 0. Perhaps gradient of V is bigger than a universal constant, which is positive. This cannot be. For example, take a theory which is supersymmetric in, for example, Calabi-Yau compactifications, and consider one of the massive fields. Sometimes these have massive fields. You go to the massive field, and you can take a vev of the field near 0, and this gives you a potential which can be arbitrarily close to 0. So that's not true. So this cannot be a correct criteria. So one can instead consider a bound of the form gradient of V is some function of the scalar fields, and perhaps a natural choice for F would be the potential itself times some constant, some positive constant. So we contemplate the possibility that we have a bound that the norm of gradient of V is bounded by a positive constant times V, where C is some number of order 1 in Planck units, presumably a universal number, which may depend on dimension, and of the form of the gradient of V bigger than or equal to C times V. So let's make a check of this statement. So gradient of V is bigger than or equal to CV is trivially satisfied when V is negative. So for supersymmetric vacua, we know that V is less than or equal to 0, so therefore, at least for those, there's no contradiction to having gradient of V being equal to 0. So this is fine with supersymmetric vacua we know. So even, also it's trivially satisfied for supersymmetric examples with zero cosmological constant. If V is zero, you could have some flat moduli, but that corresponds to the equality part of this, this relation. So that's also fine. So then we ask, how about positive value of V? So what is the right way to think about this band when V is positive? So let us start with the supersymmetric case with zero cosmological constant. For example, type 2 strings on Calabi-Yau, let's say. And then we want to deform the theory. Well, how do you deform the theory? Well, you just give a VEF to some operators, which in the context of this theory would correspond to, and if you want to go away from supersymmetric one, it means that you're giving VEF to some massive fields. So basically, you can parameterize the deformations away from the supersymmetric one by deformations of the type of the potentials of the form 1/2 m squared phi squared for phi near 0. So if you compute gradient of V over V for these examples, you get simply 2 over phi. And this is, this, as you can see, is bigger than order 1 for phi near 0. Of course, when phi is too big, you don't trust this description. In fact, you believe that phi is of order 1 in M Planck. You definitely won't have such a simple form, and you have all these other issues with getting the tower of light states. So this actually fits beautifully with the statement that the range of the fields cannot be that big for a given effective field theory. One can consider M theory in the supergravity limit and consider compactifying on to D dimensions on an arbitrary 7 manifold to 4 dimensions. So you go from 11 to 4 dimensions, pick your 7 manifold of your favorite type with arbitrary metric and arbitrary G-flux. The only thing I want to assume is that the supergravity approximation is valid. In other words, I'm not considering a situation where you have singularities in geometry or you have curvatures of the order of M Planck in G or R, so you're restricting to that kind. From the viewpoint of 4 dimensions, all the choices of the metric and the fluxes would be these scalars. So you have a potential as a function of infinitely many scalars which parameterize for a given topology of the manifold, the metric and the fluxes. Huge potential. Now, if we didn't know any better, we would have said, of course, there's going to be somewhere a critical point for that V. It's hard to believe there's no such critical point for positive V. But that's precisely what Maldacena and Nunes show. For positive V, there is no critical point. So sometimes a reasonable looking statement that if I had just told you, take a generic V and find a critical point is not correct. Okay, this is an example. And this is the no-go theorem for Maldacena and Nunes. So we shouldn't necessarily believe our intuition of what is natural is necessarily the correct one. In fact, the Maldacena-Nunes no-go theorem can be strengthened. Suppose you compactify M theory to D dimensions, one can easily show that upon using just the very boring volume rescaling, that gradient of V over V is indeed bounded by a constant of order 1. No matter what manifold you choose, no matter what metric you have, etc. So for any 7 manifold, any metric, any flux, you have a bound. So what do we say? Well, we say we try to violate it by Planckian corrections. That's what we are saying. For M theory, it's impossible to do it if you just take supergravity approximation. One-line argument, nothing fancy. Now, for D equals to 4, the bound you get from this is 1.6. And this is indeed realized in the ADS 4 times S7 example. If you go away from the minimum as a function of the radius, if you look at the potential, if you go away from the minimum, which is the negative V, to the positive values, sufficiently close to the origin, you find the slope indeed goes like this limit. So these values are actually realized in actual compactifications. If we assume the strong energy condition, which of course we know it's not true in general, or more precisely, if we consider compactifications respecting the strong energy conditions, you get a bound of this form. If you start with capital D dimensions, assuming strong energy condition is correct, going down to lower dimension D, you get grad V over V bounded by this number. And if you compactify, if you use the null energy condition, similarly, again, we know null energy condition is not necessarily true in string theory. There are objects which violate it. But if you consider compactifications respecting it, you get a bound like this. Again, you get numbers of order 1. So if you go down, for example, to four dimensions from 10D, you get number of order 1.2 for this bound. So how about other examples? Well, there is actually a non-supersymmetric example which does realize a positive cosmological constant. This is from old days, and I think the younger group here may not even be aware of this. This is called the O16 times O16 strings. It is a non-supersymmetric, non-tachyonic theory in 10D. And at weak coupling, you can compute the cosmological constant as positive and in fact rolls down like this. So you can compute it for that example again. Grad V over V is some number like 5 over root 2. So there are examples which naturally realize it with nothing fancy in 10 dimensions. Also, extending an argument of Hertzberg et al. And also Rassi et al., one can show that if you compactify type 2A or type 2B from 10 dimensions to 4 dimensions with arbitrary Ramond-Ramond flux and with OQ and DQ branes turned on, but only for a fixed Q, then for almost all these cases you get bounds of the type I just told you, including negative O branes, by the way. So this shows that for a large classes you get no-go theorems. Now this does not cover all cases, as you can see, and I'm also assuming that only a very specific Q is turned on, so I'm not turning on all possible OQ and DQ branes. But there is very little work involved in showing this statement, I'm trying to say. It's very boring little rescaling of the volume and the coupling constant. That's all that goes into these arguments. Nothing fancy. Now one can try to do more fancy things and perhaps get other things, but in other words, when these are empty, it doesn't mean that this goes to 0, but we just don't know how to find a bound. So the upshot is that the conjecture is not unreasonable with C of order 1 in Planck units. Okay? Well, this also makes quintessence more natural because now V prime of order V is not double fine tuning. It's very natural in the context of string theory. So now we don't have that objection. The two natural objections or 3 natural objections raised against quintessence are alleviated in the context of string theory if this Swampland condition is correct. So what are the cosmological implications? Well, so there's this bound I told you about, grad V over bigger than or equal to C times V. There's another bound which is discussed a while back, which we proposed with Hiroshi, where the range of scalar fields for a given effective field theory that we write down is bounded by something of order 1 in Planck units, which I call now here delta. And we believe that C and delta are numbers of order 1 in Planck units, though we don't have precise numbers here. So let's assume that these are strict true facts about quantum gravity and see what consequences they lead to. And well, there are 3 consequences we can contemplate: the past, the present, and the future of the universe. So let's go to the past. Early universe, inflation has mild tension with these criteria. In fact, the constant C that I talked about is related to the slow roll parameter in this form. And the current observational bounds on the B mode lead to epsilon less than 0.004 and C less than 0.09. However, actually, the textbook models of inflation, when combined with the spectral tilt, gets ruled out. So among the ones which are not ruled out and which are favored by some inflationary models are the plateau models. And in those cases, one finds C is less than 0.02. Well, okay, so you could say this is order 1 number or not, I don't know. So I leave that to your judgment. But at any rate, this number is getting to be a little small compared to the examples at least I showed. Moreover, the number of EFOs being greater than 60 leads to that delta bigger than 5, again, in these plateau models. Again, a little too big for comfort. This is, again, not strictly a problem, but it sounds like a little bit of a potential issue coming up. Okay, so that was the inflation, and let's talk about present. So now the fact that we are saying that you cannot be in the metastable de Sitter only allows quintessence models. Therefore, you could ask, what does a quintessence bound give you? So here, this plot here is a function, is a W as a function of Z. So this Z is the usual cosmological Z. W is the one which defines the equation of state for the dark energy component in the universe. So this black line here are the observational bounds between, so the observational bounds are the value of W is between this black curve here and -1. -1 would be the value corresponding to the cosmological constant, where you have a metastable de Sitter, whereas the observational bound are these blacks. If you just take simply a potential of the form V e to the minus C phi, and where C is a constant, you find that if the constant is 0.6 or lower, you comfortably satisfy them, no problem. Amazing that the bound, the experimental bound, gives such a number of order 1 in M Planck. This is remarkable. It's remarkable that the bound we're getting from experiment gives you the bound which is of order 1 in this M Planck units that we are discussing. So it actually reinforces the idea that not only quintessence is not ruled out, but it's actually quite natural in this context. In fact, one finds that there is a universal bound. So this was just this example of this potential. But you could say, well, what about the more general case? You find that this gives you actually the best bound that you can get. And in particular, you can show that it predicts that 1 plus W today is bigger than 0.15 times the square of that number that appears in this Swampland conjecture. So, and this CB less than 0.6 is consistent with data. So one way to check would be to compute the W. So this suggests that we should try to continue with the efforts to try to measure W, and there is not theoretical motivation to see whether it's -1 or not. How about the future? Well, if we lived in de Sitter space, the lifetime of the universe before there is a phase transition can be arbitrarily large, because we would be we presumably will be either infinitely stable or maybe some decay in the usual metastable form, but there is no relation between the cosmological constant, this energy, and the height of this barrier. So in principle, the lifetime is completely unrelated to the dark energy or cosmological constant. However, today, the lifetime today is very interestingly related to 1 over the square root of lambda. Now, people say this is the coincidence problem. This is one version of the coincidence problem. Why do we happen to live in an age where this is true? There would have been a satisfactory answer if the age of the universe cannot be much more than that, in which a typical number you sample would be of that order. So if you look at grad V, So if you look at the grad V bigger than V constraint, it's getting exciting here. Okay, I don't know how this works, but okay, I'll do it easily. So we go like this. So, so what's the future? So we are basically rolling down. We can put a lower bound on the speed of the rolling, the kinetic term of phi today, based on observations, and it's rolling. And we know that grad V over V is bigger than some constant. So therefore, this is going to somehow roll like this, or perhaps cross 0. But this cannot range more than order delta before the effective field theory breakdown with getting a tower of light states, according to the Swampland conjecture that we had with Hiroshi. Therefore, we can estimate how long does it take for this guy to roll a distance delta. And you find that the number of Hubble times for this to happen is proportional to delta over C. The delta is that other constant in the Swampland conjecture, and C is the constant that I was talking about. So these are both order 1 numbers. And you get 3 over 2, and this omega is this 0.7, is the fraction of energy in the dark energy. So this number is of order 1, which means the number of E-foldings left over before we undergo phase transition is of order 1 in Hubble time. Therefore, if you sample the time in that scale, it's related to the dark energy. So the statement is that precisely when the dark energy takes over, we're basically about to do a phase transition. That's the nature of this argument. So in other words, it is not a random time we are in. It's about the end of it. So, the argument uses the relation that if you compute the kinetic term, and if you integrate it, the kinetic term at the kinetic term now, which is x0, which is bounded by experiment, and making sure that this is the total range of the field is less than delta, gives you this bound for the range of the field. So simple argument. So I have run out of time, but let me just say what are the observational consequences. So first of all, it suggests that we should do more accurate measurements of W of Z, and we want to see if 1 plus W is significantly different from 0 today. as we are predicting. The dark sector couplings have been changing over time as they presumably couple to the quintessence field. So observational consequences of these would be apparent violation of equivalence principle in the dark sector, which would be very interesting to detect. So let me conclude. It seems not unreasonable to believe de Sitter is not realizable. So my colleague Hiroshi suggested the double negation. He liked it here. So as you can see, we are very careful here. We do not know. It could very well be that the constructions are correct. So this is just would be viewed as a speculation in that case. But it seems like it's reasonable to entertain it. As you can see, it has dramatic consequence, and it's worth exploring. And this gives you some tension with inflation. It's a mild tension. Present epoch must be based on quintessence, and there naturally fits with these ideas. And the universe is about to undergo a phase transition in order 1 Hubble time. And so I think I would say that either a tower of light states will appear or the cosmic acceleration stops. So I will stop here. Thank you.
Thank you very much. I'm sure that there are questions.
If d phi is of order phi, d refers to spatial and time variation, right?
D phi, delta phi is the variation of phi over time, for example.
Yeah. So that means that phi is changing over Hubble over Planck time?
It means that the range, so usually we take in the field theories, the range of phi is could be minus infinity to plus infinity. So what we find is that in string theory, for example, in the Calabi compactifications.
No, but you want to consider the case where d phi over is of
No, not phi, if dp, you mean.
dv.
V is the potential for the phis. So V is a function of, V is a potential for scalar fields. The question is, what are the slope for this? What's the gradient of this potential? And does it related in any way to the value of V, not phi? Phi is not the issue. So there are two conditions. That was one of them.
Have you explored what happens to fundamental constants as a function of cosmological?
So the statement is that this field would not, if this field coupled to our sector, it would be quite dramatic and it would be wrong, clearly. But as I tried to explain, that's not the necessary situation in string theory. In fact, a very typical example of models in particle phenomenology is that we have a localized sector. If you view this red geometry as a geometry of internal space, the green area is where we get our matter, and this is what happened, for example, in F-theory models in phenomenology. This could be another area. There's a dark matter. Would be, that's...
You're putting in addition to, so you're still left with the fine-tuning of B, cosmological.
Yes, no, we have not, so absolutely. So we have not solved this cosmological constant problem.
And to deal with this problem, you're putting in another
sector.
Fine-tuning.
Another sector, I would say, which is dark matter.
Yeah, no, I understand. Another sector which you assume by this mechanism or some other is exponentially suppressed.
Yes, exactly.
But that's another potential.
Not so strange in string theory. First of all, we know there is dark matter.
In this.
Yeah, so in other words, if you take the prior, in experimental prior, that there is dark matter and couples weakly to us, this is a very natural picture in string theory, given that.
This is A.
Yes, it's a natural picture.
But what's so this is a way of getting such a suppression. What kind of suppression do you need to agree with the fact that constants don't change in time? It's one of the arguments against quintessence.
Yes. So usually, for example, in string constructions, you get localized fields like in orbifold singularities.
How this is realized in string theory. What factor do you need?
Oh, 10 to the minus 6. I showed that number before. So here is the change of the fine structure constant, for example, over the period from Z to 1. It's 10 to the minus 6. So that's the suppression. It's not infinitely big, but small.
So I appreciate the kind of cautious way that you presented your argument, but still, you focus on these no-go theorems that explicitly exclude orientifold planes.
No, it included it. Sorry. No. It included
the ones which give a dip.
No.
M theory does not have these.
No, let me show you. This actually was already done in the paper by Karcher et al. As well as by Rassi et al. Here.
No.
The orientable plane are not, with a negative tension are not excluded in this discussion.
But as you also said in your comment there, you didn't include all of the possible.
That's right. Otherwise, I would have given a proof.
I'm sorry, but you didn't include the leading contribution to the scalar potential in string theory, which is the d minus d critical term, which leads to the original scenarios for de Sitter. There is also a three-dimensional model, which is pretty explicit, that came out in 2010
Yes.
with Shidong and Gonzalez-Toroba.
Yes.
So if you have an objection to the details of that, please let us know.
Okay, we can discuss it. But anyhow, I didn't want to get individual models because there are hundreds of people that I would have to respond to. But the main point is not to say they are wrong. I'm not saying you are wrong or they are wrong, but I'm just saying that the possibility, I think going over supercritical dimensions in string theory is debatable, whether that's a good thing to do or not. We have discussed that before.
Well, it's connected to the rest. There's a lot of literature on that by Hellerman and by...
Yes, but anyhow, I don't want to
So
debate...
it doesn't make sense to exclude that by fiat.
No, I didn't exclude it.
That
I just...
it is connected to the rest of the theory.
Eva, you might be right. I'm not saying you're wrong. You might be right. But this might also be right.
Just give a detailed reply to the existing models. That's...
Sandeep.
Thank you for a very thought-provoking talk. But let me just say, some of the ingredients that have gone into the kind of constructions are generic that Eva was referring to, which are not in your bounds, are generic. For example, quantum corrections. What KKLT actually illustrates, how was the Maldacena-Nunez no-go theorem evaded in KKLT? At root, because quantum corrections were incorporated.
That's a fair criticism. Some people believe, in fact, it's a fair criticism. Some people believe that quantum correction might do the job. It may or may not do the job. My only statement is that quantum corrections typically get dualized to non-quantum corrections. It becomes classical. So it's surprising that in no picture that quantum thing can be seen classically. That's already a surprise. So somehow it should be that in any classical frame, there has to be quantum correction for this to happen. Could be, I do not know, but that sounds exotic, you agree?
Well, I think we have one more question by Greg, and then we have to stop because I
have a much simpler question. So delta V over V has units, and so you said you were bounding it by order 1 in the Planck scale.
Units.
Which Planck scale?
Planck scale in 4 dimensions. So
well, but why not the 11-dimensional Planck scale?
No, in each dimension. So first of all, in each dimension, there's a bound in that dimension. The constant will depend on dimension. That's the first statement. So that's, in fact, let me bring it. So,
but these differ by functions of the moduli.
No. So you're an Einstein. No. You're an Einstein frame. Always you go to the Einstein frame. It's unambiguous statement here. You always are an Einstein frame. There's no ambiguity in the definition of the distance. And one other thing I forgot to mention.
But if you start to decompactify, then that's going to change, right?
In each, for a given effective field theory, so that's precisely why the range of the field is bounded. In other words, as long as you have an effective field theory which is valid, that means there's a bound in the range of the fields. One thing I forgot to mention is that, so to an effective field theorist, this doesn't look right. To a field theorist, you say the range of field could be arbitrary or the grad of V could be anything. But if you restore, as Greg is suggesting, M Planck here in the discussion, the M Planck will go down in the denominator. And if you take M Planck to infinity, there's no bound. So precisely when you decouple gravity, there is no bound. So this is consistent. Any Swampland criteria should be trivially satisfied in the field theories that we know, and this does satisfy that at least.
I think it's very good that we have this discussion, but I think we also have to go on. So thank you very much, Cumrun, again.
Thank you.